Right, we're back. Parallel circuits. You'll notice that I've got my single bulb back connected to the power supply. And now, instead of connecting this second bulb in series, we're going to connect it in parallel. And the easiest way to do that is put a wire from one to the other on this side, and then a wire on the other side like that. Now, you'll notice that this, I don't know if there's enough space here, this is almost laid out exactly how you draw a parallel circuit. Obviously there's no one way to draw a parallel circuit, but the way that you most often see a parallel circuit with two bulbs in it drawn is with, you know, a loop with one circuit and then a sort of loop coming off that. So that's laid out quite nicely. Now remember, with series circuits we measured the voltages across the components and then they added to the supply voltage. Well, let's try the same thing here and see how the voltage behaves. So just check the voltage of the power supply. It's 3.57 volts. 3.57 volts. It's again fluctuating, but it's gone up to 3.58. Let's settle on 3.58. Let's measure the voltage across each of these. So the first bulb, 3.50. It's fairly close to 3.58. Let's measure the voltage across this guy. Wow, 3.88. Now that is interesting. Oh, here we go. I don't know what was going on there. 3.49, 3.51. 3.50. So both have about 3.5 volts across them, which is slightly less than the voltage across the power supply. Now, if you've watched my other video, you will recall that there's a reason why we might not get the full voltage drop appearing across the bulbs. You notice how this bulb keeps going off. Okay, that's what was affecting my readings. Okay, so you see, this is not, this is completely genuine. I'm not editing this overly. So, voltage across the power supply was, okay, it was, well, it's gone up now, 3.62. 3.6, so it can't decide. Anyway, the voltage across these two was not far off. It was 3.5. Now the reason we're not getting the full power supply voltage is, again, because we're ignoring, or we have to take account of any voltage drop across the wires. Now in an ideal world where you ignore the resistance of the wires, you'd expect the full power supply voltage, the 3.6 volts, to appear across this bulb and across this bulb. Okay, as it stands, this is a real circuit, so we're not going to get perfect results. Let's now measure the current. I'm going to first of all place the ammeter before, like right next to the power supply, before either of the bulbs. So let's measure the current, the total current flowing through the circuit. Now, remember, I need to change the setting on the multimeter. We'll change that setting, and we're going to measure 0.53 amps. Remember that number, 0.53. Because now I'm going to measure the current through just this bulb, through this branch, by removing this connection and putting the ammeter next to, adjacent to this bulb. 0.26. 0.26 amps through this bulb. Okay. 0.26. Let's see what we've got through this bulb. Make sure it's connected. 0.25. So we've got 0.26 amps through this branch, 0.25 amps through this branch. They add to 0.51 amps, and the total current back here, I think it was 0.53, wasn't it? I did tell you to remember. So you can see that these currents roughly add to the total current in the circuit. Again, this is a real circuit. I'm using real equipment. You can see that this lamp's pretty dodgy, but the current in a parallel circuit, unlike a series circuit where the current's the same throughout the entire loop, in a parallel circuit the current splits. And therefore the current through this plus the current through this is equal to the total current in the circuit. Okay, I hope that's given you a little bit of a physical, like realistic idea of how circuits are built and how they work, something that you won't get necessarily at the moment. Okay, thank you very much.